So this is the final video of the Nature of Light series for the grade 10 students. And what we're going to look at finally then is a little bit of the consequences. We've been dealing with some pretty, theoretical kind of non-everyday concepts. So I wanted to kind of bring it back and show you how some of this plays out. So we're going to look at electron traps, and we're going to look at some applications. We're going to talk about quantum tunneling, and we'll look at some applications of how that affects us in our daily lives, not just something fancy in the laboratory. And that will end this description of the nature of light, and I hope you've enjoyed it. Now let's retreat for a moment in this final part of the story here to just to put a little bit of comment. This has all been kind of dry. So let's look at some, first we'll call something called electron traps. And this is any circumstance where an electron is bound. So, like an atom, okay? The electron is, under general circumstances, stays with a particular atom. Let's keep it simple and we'll do a one-dimensional approach. So if we have a graph like this, and here we have energy, and here we have position. We're doing a 1D situation. And we have a trap such that the energy at one place here and somewhere else here, in this case, when I say this is infinite, okay, then the probability of the particle must stay within here. Okay, so this is probability of location. And because it's infinite, the particle can't escape. Now, let's suppose, but of course that's not a real life situation. No atom has an infinite capability of holding another electron. So let's modify this a little bit. Now we're going to make it finite. And we're going to have the energy will do something like this. So here we go. This is our potential. And then the energy of the particle sits somewhere in there. Now here's where we start to get back to visiting the uncertainty principle. Because what we're going to say here is that the particle, when it gets to the corner, and we'll zoom this right in here, okay, if the particle gets to the corner like so, okay, what is happening? Well, the location is known. And when it is constrained in 2 dimensions like this, when the particle hits the corner, its speed equals 0, and that's known. And this is a problem. And you might say, okay, this is a violation of the uncertainty principle. Now you might say to me, oh well, it's just because what the problem we make the mistake of is we think of these things as bingo balls or something like that when they're not. These are subatomic particles, and the quantum world is not the world we live in. So we got to be very careful about those types of analogies. All right. So let's look and see what happens here. So we're going to have to make some space here. Now the uncertainty principle is going to tell you something that you're not going to believe. And so we'll just draw this again. So here's our potential on either side. And what we're going to say is that the energy of this particle is now, so the energy, let's not say it that way. Let's say the possible locations includes a small amount of the forbidden barrier. The uncertainty principle is fundamental. So you have this particle in a box here, but that corner is not permitted. So as a consequence, the particle is allowed to exist in a small fraction of this potential barrier here to alleviate this conflict with the uncertainty principle. And you might say, well, this sounds complete silliness. And I would agree, when you first hear it, it does. However, this is how nature is constructed. And what I think I'll try to do to give you some context is to give you a couple of real-life examples of where this happens. Well, before we do that, let's just make one more adjustment here. Suppose this barrier, however strong, is very narrow. Okay, so we have a very high potential barrier, but it's not very wide. Now we can see that the particle can escape. The escape is possible. And we call this quantum tunneling. Now, the whole thing sounds completely science fiction, and you could be forgiven if you think it is so. But let's look at a couple of examples that you may be familiar with that show the efficacy of all this. Okay. So the first one is radioactivity. So we have uranium-238 will on its own react to form thorium-234 plus an alpha particle. This is a natural phenomenon. But let's imagine we have the huge, in comparison, uranium nucleus. We have 92 protons here. And so the strong force binds the protons. They don't get to escape. But it is a very short range. So by probability, if you're patient, you will get a situation where we end up with a small group where we have 2 protons and 2 neutrons that find themselves outside the nucleus. Now when that happens, we must remember that electrostatic forces are enormous. So what we have here is 90 protons pushing against 2 protons, and these are sent away at an enormous rate. We call this alpha decay. And it happens because of quantum tunneling. That's how they escape the nucleus. Alright, you might say to me, fair enough, but I haven't really spent a lot of time with radioactive substances, and this doesn't mean very much to me. And I can accept that. So let's take something else that perhaps means something to all of us. How about the sun? We all kind of depend on that. We all look at the sun. And in general, we take 4 protons and they are combined to make 1 helium nucleus, which is 2 protons and 2 neutrons. Now the problem with this is that protons are light and are highly, I emphasize that, repelled, as they have like charges. So in the around 1920 or so, they calculated that a ball of gas of the sun's size would have a temperature at the center of somewhere between 5 to 10 million Kelvin. However, to combine 2 protons at the rates, at solar rates, okay, we need to have 100 million and perhaps 15 million atmospheres pressure. This is not possible with the mass of our sun. Okay, fine. We can accept that it's not possible, but then the question begs, if it's not possible, if the sun's core is not hot enough for protons to combine, then why does the sun work? So the core temp is roughly 10% of the required value. And the core pressure is, depending on who you talk to, somewhere between 20 to 50% of the required value. And so then let's look and see what each of these parameters do. The temperature is kinetic energy, basically. So as the temperature increases, the speed effectively increases. And this controls how, quote, hard, for lack of a better word, the protons collide. The pressure does something else. The pressure is in effect, in this particular case, is a containment. And it begets also density as well. So this gives us more targets. In a given space. Now, if you combine these two, if it's fair to do so, we're looking at probabilities of the hydrogen combining to form helium based on the non-quantum version of maybe only 1 or 2%. Now, that's what I'd say wouldn't happen, but it's not going to happen very often. What we learned in into the 1930s was that the proton-proton chain could work because of quantum tunneling. That all of this is going on, and though it's nowhere near enough, there is far more interaction because of quantum tunneling cases than there would be if it was simply straight energy. And this allows for this reaction to occur at much lower temperatures and pressures than would otherwise occur. And the sun occurs and runs at this mass level and circumstance. So we have a lot of really interesting aspects to this entire story of how first the speed of light was discovered and measured, and then our initial understandings of how atoms, their true nature. Now, understand that textbooks have been written about this topic, about even aspects of this topic. And this was only intended as a brief introduction for students of science in their grade 10 year. Well, hopefully you enjoy this. Hopefully you can remember some of these ideas as you learn more details about these different aspects of the quantum world. Thanks for watching. Well, there you have the initial story of how quantum mechanics began, and again in a primarily non-mathematical way. We look at electron traps, we look at how electrons can be confined, we look at quantum tunneling, and this then brings in notions of how basic radiation works, which of course takes us back to 1896, and also talks about even something straightforward as our sun and how it works and is based on these very interesting concepts, and why astronomy and astrophysics are such an important subject, because in comparison the research is fairly inexpensive, and yet by looking at the very big we learn about the very small. Anyhow, I hope you've enjoyed this series, first on the speed of light and then on the nature of light. Thank you very much for watching.